Yes.
Welcome to NeoScribe. What do these old devices have in
Is it
common?
also audible?
Wire.
Is the audio available?
Yes, audible also.
With the exception of major appliances, the evolution of electronics is wireless technology. We even receive the internet wirelessly, and we're starting to charge our phones wirelessly. And as vehicles become electric powered, it's safe to assume that wireless charging is the inevitable path. Imagine a future where electric vehicles charge wherever it parks, while stopped at a traffic light, or even as it drives along the highway. This would finally put an end to range anxiety, and is possible by electromagnetic induction. Electromagnetic induction involves two electromagnetic coils, which are simply wires, usually made out of copper, that are wrapped around a core and have electric currents running through them. One coil is a transmitter, which in the future will be on a charging pad in a parking space, at a stoplight intersection, or even embedded in the road itself. And the second coil is below the vehicle, serving as a receiver. And as electricity passes through the transmitter coil, it generates a magnetic field and transfers energy to the receiver coil, charging the vehicle. So industry experts believe that wireless charging for electric vehicles will be implemented in 4 phases. The first phase is simple residential systems. Second, wireless systems will emerge in parking lots. Third, on-street parking spaces. And then fourth is farther out into the future, when we will see dynamic wireless charging systems embedded into highways. And the first phase is already unfolding, as there are at least 2 companies that have already developed residential-grade wireless charging, including Evitran and Witricity. Evitran is based out of Virginia and has wireless charging systems available for the Tesla Model 3, the BMW i3, and the Nissan Leaf, with various output levels between 3.3 to 7.2 kilowatts, which is around the typical home power rating range. Witricity is based out of Massachusetts, and their system stands out because their output ranges up to 11 kilowatts. On top of that, auto manufacturers themselves are developing their own wireless charging systems, including Nissan and BMW. While phase 1 of wireless charging appears to be well on its way towards implementation, but phase 2 through 4 will need government support. And this brings us to the UK. Back in July, the country proposed a plan to dedicate £40 million towards research for wireless charging technology. This includes investigating wireless charging solutions for streets where off-street parking is not available. And they also want to research wireless charging solutions for commercial vehicles, such as ride-sharing service vehicles and delivery vehicles. So I'm excited to see what comes from this research, and if it's even half as compelling as the US Department of Energy's research, it's going to be amazing. The Department of Energy-sponsored Oak Ridge National Laboratory has recently demonstrated a wireless charging system with an output of 120 kilowatts, which is equivalent to a Tesla supercharger. And the lab isn't stopping there, as their long-term goal is to develop a wireless charging system with an output of 350 kilowatts. This would allow electric vehicles to charge in 15 minutes or less. In order for dynamic wireless charging systems to be economically viable, meeting the 350 kilowatt goal is critical. You see, as the power output improves, the number of coils needed to be embedded in roads is reduced, along with the cost to install. So hopefully Oak Ridge can continue to make progress and make it possible for wireless charging to happen while we're driving down the highway. In the meantime, we can already see a dynamic wireless charging system in action with a demonstration project done by Qualcomm Technologies. Qualcomm constructed a 100-meter test track in France embedded with a 20 kilowatt wireless charging system. While 20 kilowatt output is not nearly powerful enough to be economical, it's still awesome to see, and it shows that dynamic wireless charging will someday be a reality as the technology improves. And it shows that with wireless charging technology, it's only a matter of time until we see the end of range anxiety.
Moving on to regenerative braking now. Let's start with this small video wherein this guy is coming downhill and he's saying that his car is getting recharged while the vehicle is always already running and covering few kilometers, but battery is getting charged.
standing by one of the newest tourist attractions in Norway. It's called The View. They made a quite spectacular thing up here. And we're about 700 meters above sea level, and we're going all the way down here. And the funny thing about Tesla is that it makes also power. It gives us back the kilometers that we lose when we go up. So we are going all the way down here, and we're going to check out how much we gain. So that will be funny. Now, of course, for this to work, you need to put your regenerative braking into standard. If you put it into low, nothing will happen. You will not gain any electricity back, and you have to use your brakes all the time when you're going down a steep hill. But if you put it into standard, then of course the car will brake by itself. It will regenerate the power back to the battery, and also you will save a lot of your brake pads. Okay, here we go. It's also very important to watch out for sheep in the road. Other than that, this trip will be perfect. Now I'm 0 meters above sea level by the fjord, as you can see. So let's check out and see what has happened with the night rider. So you see, all green and regenerating all the power back to the vehicle. And we started with 271. And now we have 283. So actually 12 kilometers we gained in 13.6 kilometers. That's quite funny. Of course I had to use a little bit power at the end, but you get my drift.
So this is possible through a regenerative charging system, also known as kinetic energy recovery system, KERS. Amount of regenerative torque to be used is determined by considering motor capacity, how much capacity do we have, how much bandwidth do we have, battery state of charge. So usually 75% is upper limit. In some cases 70%, 80% is what is the upper limit for which the regenerative braking or regenerative charging is possible. After 70%, 75% of capacity of the batteries, regenerative braking is not recommended and not done by the controller. And this is because of the obvious reasons that during regeneration you get a very high amount of energy surge coming towards the battery. And as we studied during the earlier session of charging of the batteries, that it is not recommended to charge the battery at very high current rates after 70% of its capacity. During its constant voltage region, the current acceptance is low. Battery max input current, that is C rate of the battery for given SOC level, so that has to be known, and based on that the regeneration is tuned, and at the same time vehicle velocity as well. So sometimes, when the vehicle velocity is low, again, there is the time when regeneration is not possible, because through regeneration, you might get a voltage which is very low, which is not enough to charge the battery at lower velocities like 20 or 30 kmph. Above that, regeneration is possible, and that is possible only when SOC is less than 70% of the capacity of the battery. The working is very simple. Regenerative braking system recovers as much kinetic energy as possible and stores it in electrical energy. So basically it applies brake through motor. In this case, motor is disconnected from the system which is giving power to the motor. So we must have also seen or kind of discussed about during the motor session that the motor runs as a motor when the magnetic field is kind of running further to the rotor. So if the rotating magnetic field is having higher RPM than the rotor RPM, then it works as motor. When the magnetic field is preceding the rotor, in that case it runs as generator. So during braking, you just have to make sure that the magnetic field is behind the rotor speed, and that way the phases are adjusted such that the energy can be generated through this motor components and the motor works as a generator. When braking the vehicle's electric motor functions as a generator, producing electricity and feeding it to the high voltage battery. So when you apply current to the motor, it works as a motor and gives torque to the wheels. When you draw current from the motor, then this motor runs as a generator and applies brakes on the wheel, kind of takes the kinetic energy from the wheels. So as soon as the kinetic energy is taken from the wheels, the wheel velocity will come down, and that is called as braking through KERS system. This video also again explains the working in better fashion. Okay, it's not running once again. There seems to be a problem with this video as well. But I have explained you how does it work. So basically the motor runs as a generator by switching the phases such that the EMF is the rotating magnetic field is behind the rotor speed, and that way you can run the motor as a generator. So the components of the motor and generator are same. It depends on what kind of speed and what is the speed of the RMF and what is the speed of the rotor. That is what is defines whether the motor is generator or a motor itself. Control logic is like this. When you press the brake pedal, so this is again one of the control logics with the brake pedal. There is also another control logic without brake pedals. So we'll also talk about that. With brake pedal, as soon as the brake pedal position change is sensed, when you apply force on the pedal, the total brake demand is kind of evaluated by the brake control unit BCU, and then the rear and front braking force allocation, the torque which has to be applied, the braking torque which has to be applied on the front wheels and rear wheels, that is decided by the controller, and then it applies it by brake by wire system. And there is also a feedback loop. The speed is reducing as intended by the controller or not, and then the total braking is either through the total braking is a combination of hydraulic braking plus regenerative braking. So you are running brakes and running the regenerative brake and the hydraulic brake, that means mechanical brake, at the same time in most of the cases. There is also another type of technique wherein regeneration is done. that is called as single pedal driving. In case of single pedal driving, the only change is that it doesn't need brake pedal input. What it needs is a ac pedal input. Let me just see whether it is already discussed in further slides. Okay, not. So it needs ac pedal input. As soon as the ac pedal is released, that means there is no input on the ac pedal, no force applied on the pedal. As soon as it is released, then the brake control unit comes into action, and there is no hydraulic braking applied. Actually, there is only regenerative braking is applied. And the control logic, other control logic remains the same. As soon as the accelerator pedal is removed, as soon as the ac pedal foot over the accelerator pedal is removed, the accelerator pedal comes to 0 position, and then the brake control unit applies regenerative braking through motor, which works as a generator. And so this motor then working as generator gives energy to the battery pack. Again, there are few power electronic components in between, which will change the voltage of this generator to voltage which is suitable for the battery, for charging the battery, and then it is supplied to the battery pack. Brake blending, it is a kind of mixing of the braking force, which smoothens the whole braking phenomena. Why is it done? It is done so that this mixing two different brake systems to give the combined result, that is, which is expected by the driver. So a driver which is coming from a IC engine vehicle wherein the braking used to be only mechanical braking. Now, when there is also a regenerative braking involved, in that case, the experience has to be same. The experience of when I press the brake pedal, depending on how fast do I press it, depending on what kind of situation I am into, the way brakes behave, the hydraulic brake and the electric brake through motor, that behavior should be as intended by the driver. It should not be late braking or should not be early braking. And this is done through brake blade blending, wherein the amount of torque which is kind of reduced by the hydraulic brake, amount of energy which is taken away from the system by hydraulic brake and by the electrical brake through motor, is mixed such that both together gives the experience of only hydraulic braking. So friction brake, as you can see, is giving you the dotted line. Regenerative braking is giving you this solid line. The total braking force is what is the one. If you draw it, it will look something like this, and this should be as intended by the driver. Okay, addition of these two. Brake blending methods. So there is a parallel method wherein friction regenerative braking gets applied in parallel. Such strategy is disadvantageous from energy efficiency point of view, because part of the energy is being converted into heat by the braking pads, hydraulic braking pads. On the other hand, it is important, good point is the lack of necessity of the interference of the braking system. So this is where the control logic, even if it is not so good, as the hydraulic brakes are always getting applied, this brings in a safety element and the robust operation of the braking system. And another good thing about this type of braking system is it can be added to a conventional braking system. So both the hydraulic and the electrical brakes, they get applied at the same time. Hydraulic by mean mechanical brakes, and electrical by means motor regenerative brakes. However, it could compromise the pedal feel, hence requires more work in achieving good torque blending. So here, the brake pedal, which used to be only hydraulic system, only mechanical system, had to be will have to be replaced with brake by wire, and then blending has to be done. Another one is series one. So wherein the regenerative brakes kicks in first, and in the serial or series type of blending, what happens is regenerative braking comes into action first, and when the regenerative braking capacity of braking, as in the amount of energy it can take out during particular period of time, it runs out, then the mechanical brakes come into action. So regenerative brakes take precedence to the friction brakes. This is relatively complex, and at the same time it gives too much reliance on the control system. Brake by wire system has the potential to provide most consistent pedal feel due to higher level of controllability in case of series blending. In more mainstream braking systems, the total braking force and adhesion may be controlled by means of ABS and ESP or EBS systems, wherein the braking force on different wheels is being controlled by these systems, and at the same time making sure that the vehicle is safe, and braking is not creating unwanted phenomena like rotation of the vehicle itself on the ground, skidding of few wheels, a couple of wheels, and other wheels remaining on the ground like that. So these different systems, ABS, ESP, and EBS, so all these can be implemented through brake by wire system easily. Effectiveness ratio, estimation of recovered energy is very important. Just read through this. At design stage, since it helps to find out which scheme is more effective for a particular type of vehicle. Effectiveness of regenerative braking for various regenerative strategies can be estimated, and then you can find out whether the strategy which you have decided in series and parallel combinations, whether that is giving you the right amount of braking torque or not, and then the blending, whether it is giving enough braking effectiveness. That is what is studied during the design phase itself. A trip meter, which is just like trip meter on the IC engine vehicles. 30% of the battery energy is recaptured using regenerative braking, and idle time, kilometers run, consumption of the vehicle, how many kilometers per kilowatt hour, how many watt hours per kilometer consumption. So a trip meter which is giving you all this data can be useful in judging how the vehicle driver behavior is, how the vehicle has been behaving itself, and so on. Performance evaluation through efficiency and effectiveness. How well regenerative braking captures the lost energy from the braking. That is what is studied in efficiency of the regenerative braking. Effectiveness for whether does it stop the vehicle within the distance which is recommended. Does it measurably increase your range or not? And at the same time, as I said, stopping distance as well. So all these things will give you comparison between how KERS is doing with respect to the other KERS system or conventional braking system, friction braking system. Pros and cons of regenerative braking. increase overall energy efficiency of the vehicle, increases lifespan of the friction brakes, cuts down on the pollution because there is energy which is regenerated, recuperated from the braking. So obviously the electricity generation loss, pollution due to electricity generation. In case of some IC engine hybrid vehicles, again kinetic energy recovery system has become a kind of unavoidable part of the system now. So whether it is mild hybrid system, medium hybrid system, full hybrid system, KERS is always a part of the system, and this gives rise to reduction in the pollution through burning of the fossil fuels in the IC engine vehicles again. So you have advantage on both the sides, whether it is EV or whether it is IC engine vehicle with hybrid. Decreases maintenance of the mechanical parts. So in case of again EVs and at the same time IC engine vehicles. On the limitation side, highly dependent on the terrain and efficiency of the subsystem. So if terrain is like what we saw in that video, then you have very high amount of energy regeneration. While in case you come across roads which are not having, which are flat roads, then you might not get benefit of the regeneration a lot. Complex circuits are involved that add weight and cost and maintenance. Friction brakes are still necessary because that you cannot do away with. It is for a redundant safety system is what you need friction brakes. And at the same time, as I said, after the vehicle reaches to 30 kmph or 20 kmph speed, then the regenerative braking is not useful. It cannot create that much voltage. You cannot charge the battery. So the energy cannot be taken away from the system. That means the braking action is not taking place when the speed is less, and that is where again friction brakes are still necessary. So that was about it in today's session. If you have any questions, we can take them up.